Hello everyone. Today I'll be talking about the paper ARC-LfD, using augmented reality for interactive long-term robot skill maintenance via constrained learning from demonstration, by myself, Matt Lubers, and my colleagues at the University of Colorado Boulder, Connor Brooks, Carl Mueller, Dan Safer, and Brad Hayes. In the coming decades, as autonomous robots expand their scope from precision tasks on assembly lines with rigid tolerances towards small-scale factory or even household settings, there's a desire to have multifunctional robots that can perform novel tasks as they're required. To achieve this, there's a need for robot training methods that are accessible to non-programmers, and that allow a robot to quickly acquire new skills or adapt to changing environments. This is the goal of Robot Learning from Demonstration, or LFD, a suite of techniques that move away from expert programming in favor of robots observing and mimicking the task behavior of a ground truth human teacher. To obtain these behaviors from the human teacher, a number of techniques are used, ranging from methods that provide data in the robot's own configuration space, like kinesthetic manipulation or teleoperation, to observation methods that require finding a correspondence between the human demonstrator and robot learner. Unless a simple replay of the teacher's demo is all that's desired, LFD methods then proceed to create a more generalized model of the task, often relying on data from multiple demonstrations to do so. LFD is a simple enough concept to understand, but there are practical hurdles that hinder its lofty goals. Ideally, an LFD system should be easy to use. After all, LFD systems are meant for non-experts. But in practice, these methods often end up requiring a different type of expertise. Providing high-quality demonstrations is hard, regardless of the interface used, and most LFD methods require several demos to be effective, leading to an overly cumbersome learning process. Next, a robot should be able to learn generalized skills via LFD, adapting robustly to changes in environment or task configuration with ease. This turns out to be extremely challenging in practice. Human demonstrations are a low bandwidth signal attempting to capture a high-dimensional skill. Even small changes in starting conditions or task specification can require a wholly new set of demonstrations to successfully learn. Lastly, an LFD system should be verifiable. A user should trust that a robot will do what they intend it to do before deploying it. This quality is rarely addressed in LFD systems, and when it is, it almost always requires a simulator with a high-fidelity model of the environment, which substantially increases the difficulty in getting such a system up and running. Without verification, guess and check methods are used, which may be unfeasible for deployed robots which need to avoid damage to themselves or their environment. To address some of these issues, we introduce augmented reality for constrained learning from demonstration, or ARC-LfD, a system and novel approach to LFD that combines an augmented reality interface with constrained LFD to enable users to teach a robot new skills, as well as verify, repair, and edit existing skills on the fly, mitigating problems arising from poor quality demonstrations or changes in the environment or task procedure. As the back end of our system, we use Concept-Constrained LFD, or CCLFD, an extension of kinesthetic keyframe-based LFD that allows for the addition of high-level constraint information to demonstration trajectory data for use in the learning process. These constraints can encode concepts like keep the cup upright, which aren't explicitly modeled by robot state data alone. Through the application of these constraints to sections of a skill trajectory, restricting the learned skill's keyframe distributions, CCLFD can achieve task success in far fewer demonstrations than standard keyframe LFD, and has built-in resiliency to poor quality demonstrations. At a high level, ARC-LfD consists of two primary subsystems communicating via ROS. The CCLFD subsystem takes as input kinesthetic trajectory data as well as applied constraint data, and produces constraint-compliant motion plans for the robot. The AR subsystem, implemented on the Microsoft HoloLens, allows users to visualize the key concepts of the learned skill, both the trajectories and the applied constraints, in situ, thus serving as a validation step, as well as allowing users to directly shape the learned skill by creating, editing, and applying constraints to keyframes along the trajectory, allowing them to adapt existing skills to changing environments or task specifications without requiring additional demonstrations. Before showing ARC-LfD in action, we'll first step through the interaction flow as a user attempts to teach a skill to a robot. To begin, the user supplies demonstration trajectories to create an initial keyframe model. That model is then able to be visualized in the robot's environment via the AR interface. The user then assesses where constraints are needed to shape the skill, and either edits existing constraints or creates new ones from templates, assigning them to specified keyframes. ARC-LfD then adapts to the changes in constraints to produce a new constraint-compliant keyframe model, which is revisualized. If the user is now satisfied with the expected behavior, the model is kept and the skill can be run on the robot. Otherwise, steps 2 through 4 can be repeated until the user is confident the robot will perform as intended. Keyframe LFD produces a coarse trajectory of waypoints that the robot must follow. By sampling a sequence from the keyframe model, ARC-LfD can provide a visual representation of the robot's expected trajectory, showing each waypoint as a hologram of the robot's end effector. The holograms are colored in a gradient to give the user a sense of keyframe ordering in situations where it isn't obvious from context. The first keyframe is the most saturated, and the final keyframe is colored gray. Key to the functionality of ARC-LfD is the use of constraints. These constraints are simply Boolean predicates applied to keyframes, and most of them are parameterizable. These constraints can cover a wide range of possible concepts, from restrictions on the robot's kinematics or dynamics, to more conceptual constraints dealing with relationships between objects in the environment. A deployed instance of ARC-LfD would have several of these constraint types implemented as templates for the user to parameterize and apply. For our demonstration, we implemented 3 constraint templates. First is the height constraint, indicating that a robot's end effector should remain above or below a plane. An instance of this is visualized on the left, as a purple plane with upward-facing arrows, when the user selects the keyframe highlighted in blue. In the middle is the orientation constraint, restricting the rotation of the robot's end effector to a selected orientation within a given affordance angle, visualized as a cone and fan. On the right is the over-under constraint, indicating that the robot's end effector must stay within the cylinder. Notice that the selected keyframe is outside the cylinder, and is thus highlighted in red rather than blue, alerting the user of a constraint violation. Users edit the parameterizations of existing constraints or create new ones from our 3 templates using the constraint editing menu. Once these new constraints are saved, they can be applied to a keyframe or set of keyframes using the constraint application menu. Following this process, hitting the Send to Robot button on the main AR menu will trigger the CCLFD system to relearn the skill, compliant with the new constraints, and send an updated visualization to the user's HoloLens so they can verify the changes. We'll now take a look at ARC-LfD in action. As you can see, ARC-LfD allows robot trajectories to be superimposed as visuals embedded into the robot's own workspace, with individual keyframes represented by end effector holograms. This type of in-situ interaction allows for far improved situational awareness over existing monitor-based methods for visualizing trajectories. Here we see a new constraint being created from the orientation constraint template. And here we see that constraint being added to a selected keyframe in the trajectory. The typical interaction flow for ARC-LfD looks something like this. First, the user provides initial trajectory data kinesthetically. Next, the user visualizes what the robot has learned. Now, with this environmental barrier present, the addition of a new height constraint throughout the center of the trajectory will ensure it won't be collided with during skill execution. The keyframe model is relearned and revisualized, demonstrating to the user that the path will be collision-free. The user then approves the skill for deployment to the robot. To demonstrate the novel capabilities of ARC-LfD, we developed 3 case studies, each of which involved learning a general-purpose skill in an empty environment, and then constraining it to succeed in 2 different environment or task setups without requiring further demonstration. Our first study was a cubby kitting task, where the robot was confronted with changes in task procedure. The robot was tasked with placing a large rectangular object into a cubby, either horizontally or vertically. The same skill was successfully constrained to either setup via an application of an orientation constraint near the end of the trajectory, changing the rotation of the robot's end effector. Our second study was a pick-and-place task, exploring how constraints could allow for the handling of new environmental obstacles. In one setup, the robot had a clear environment to work in, but in another, a tall obstacle blocked the center of the trajectory. The application of a height constraint allowed for successful execution in this new environment as the robot steered clear of the obstacle. Our third study was a cup pouring task, where the target receptacle changed locations between trials. Using the same demonstration data, over-under constraints led to task success for both goals, as the robot waited until it was above either receptacle before beginning its pouring motion. To summarize, ARC-LfD in its current state provides multiple improvements over the state of the art, representing a step towards practical, real-world-ready LFD systems usable by non-roboticists. First, the in-situ AR visualization relaxes the requirement of a simulator with a high-fidelity environment model for verifying learned LFD skills. Second, ARC-LfD provides an improvement over CC-LfD in that constraints can be applied in a post-hoc, interactive manner at the user's own pace, rather than requiring constraint annotation during kinesthetic demonstration. And lastly, ARC-LfD relaxes the static environment assumption often required for successful deployment of LFD systems, as skills and constraints will always be visualized in the robot's true environment, not just the one it was trained in. ARC-LfD enables direct skill validation, repair, and editing without requiring further demonstrations, allowing for simple, long-term skill maintenance as environments and task requirements change over time. Thanks for watching, and if you have any questions, feel free to send me an email at matthew.lubers@colorado.edu.